As we talk about solutions, there are a couple of things we need to keep in mind. We need to recall that solutions are defined as being a homogeneous mixture, meaning that they are the same throughout. They are uniform. So we've got the same composition of components dispersed throughout that mixture. The solution consists of a solute and a solvent. So the solute is what we dissolve. The solvent is what does the dissolving. And they interact through intermolecular forces. Now that solute and solvent on their own have particular properties based on their individual intermolecular forces. Now when we mix them to form that solution, in some cases we may get some changes in our properties as a result of those intermolecular forces. Now those changes or those properties that change, we're going to refer to those as colligative properties. So colligative property is a property that changes in the presence of a solute. Now that change depends on the amount of solute present, and the amount of solute present depends on the nature of that solute. So we need to look and see if our solutes are electrolytes versus non-electrolytes. So we've got to recall some terminology from first semester chemistry. Electrolyte is going to produce electricity. It's going to generate or conduct electricity in solution. And we do that through having ions. So electrolytes produce ions in solution. We have the example of sodium chloride here. If I were to take solid sodium chloride and I dissolve it into water, the intermolecular forces, so I have an ionic compound interacting with the polar water molecule. I have my ion dipole forces interacting. And those ion dipole forces are strong enough that they're actually going to break the ionic bonds. And the result of breaking those ionic bonds is that I get individual ions in solution. So for every 1 unit of NaCl I start with, I get a sodium and a chloride separated in solution. So for 1 mole of sodium chloride, I get 1 mole of sodium plus 1 mole of chloride, giving me 2 moles of ions. Now, a non-electrolyte is going to be something that does not produce electricity. And it can't produce electricity because there are no ions present. We have to have charge to produce electricity. So my non-electrolytes are going to come from molecules. And these molecules, they do not break apart, so they're producing only molecules in solution. So we have the example here of C6H12O6, so glucose or sugar. We've got this solid here. If I take that solid sugar and I put it into water, water's not breaking the individual bonds. There are no bonds broken. The carbons stay bonded to the carbons, hydrogen's bonded to the carbons, the oxygen bond still stays there. There are no bonds broken. Instead, what we're looking at with that sugar molecule is I would have molecules stacked on top of one another that are attracted through those partial charges. So what's happening here is we are breaking the attractions, breaking the intermolecular forces, but we are not breaking bonds. So if I start with 4 molecules of sugar here, they're going to break up into 4 molecules of sugar. The bonds aren't breaking, so I'm not releasing 6 carbons or 12 hydrogens. It's still being bonded together. They're just not stuck to other sugar molecules anymore. So the consequence of this is that a 1 molar solution of sodium chloride would have twice the number of solute particles as a 1 molar solution of glucose because the sodium chloride breaks into ions. Twice the number of particles will have twice the effect on our colligative properties. So when we talk about colligative properties, we talk about 4 common properties. We've got vapor pressure lowering, boiling point elevation, freezing point depression, and osmosis. So with vapor pressure lowering, we're not going to go into this one in too much detail. We're just kind of going to get the general concept of it. And so vapor pressure lowering means that the presence of a solute lowers the vapor pressure of a solution. So that means that vapor pressure, remember, if I'm dealing with a solution with a liquid solute or solvent, they can evaporate. And that evaporation produces gas above the solution, which generates a pressure. That's our vapor pressure. So the vapor pressure above a solution will always be lower than that of just the pure solvent. We can think about why. The attractions between the particles may prevent some of those solvent particles from escaping and forming gas. generating less pressure above. Now, the extent of the impact of the solute depends on the solute's volatility. So if that solute can evaporate as well, then we're going to see that we're going to have more pressure. So non-volatile solutes, such as solids, have a larger impact, so they have a greater lowering of the pressure than volatile solutes, such as liquids. Now, our next intermolecular force we've got is boiling point elevation. So this indicates that the presence of a solute raises the boiling point of a solution. So that means that the boiling point of a solution will always be higher than that of the pure solvent. So if I've got water, water boils at 100 degrees Celsius. If I add sodium chloride or I add some sugar to that water, the boiling point will raise. Now, how much it raises depends on the solution concentrations and the number of particles present. And we see that relationship based on this equation. I've got that delta TB, so the change in boiling temperature, equals Kb times m times I, where Kb is our boiling point elevation constant. It depends on the solvent identity. M is our concentration. So we said the change depends on concentration. M is our concentration. And remember that that is the concentration in molality. And then finally, I is what we call the Van Hoff factor. I is the number of particles dissolved in solution. If we're dealing with a non-electrolyte, then I is going to equal 1. So we just looked at that with the sugar molecule. For every 1 mole we start with, we get 1 mole of molecules, so I is 1. But if my substance is an electrolyte, like that sodium chloride, then my I value is going to equal my total number of ion moles. Now, next we've got freezing point depression. Freezing point depression tells us that the presence of a solute lowers the freezing point of the solution. So the freezing temperature of the solution will always be lower than that of the pure solvent. So again, if we talk about water, water freezes at 0 Celsius. If I make a solution, that solution now freezes at a temperature lower than 0 Celsius. The change in freezing point, just like the boiling point, depends on the solution concentration and the number of particles. And we see a very similar equation. We get delta TF equals KF times M times I, where delta TF is just the freezing temperature. KF is the freezing point depression constant. It depends on solvent identity. And then again, M is the concentration in molality. I is the Van Hoff factor, and just like we said in the previous slide, that's the number of particles dissolved in solution, which depends on electrolyte versus non-electrolyte. So our K value, so concentrations, molality, we're going to have to calculate molalities. K is a constant. The K depends on the solvent. Now here we've got the K values for water. We've got the freezing point depression constant, the boiling point elevation constant. Both of those equations were the same. The only difference in determining freezing change versus boiling change is what K value we put in. So if we're looking at freezing point change, we're going to use KF. If we're looking at boiling point change, we're going to use KB. So thinking about colligative properties, we actually encounter colligative properties in our daily lives. And one example is the fact that we put salt on icy roads and sidewalks in the winter. So we're being asked here in problem 1, what does that salt do in terms of colligative properties? So if I have salt on my sidewalk, or I have ice on my sidewalk, that water would be a solvent. If I add salt to it, we're going to start to get a mixture. We're going to get a solution forming. That solution has a lower boiling point. So what that salt does is it lower freezing point. And so the salt lowers the freezing point of water. So we can add that salt onto sidewalks that are already icy because it will cause it to melt, because once that solution forms, it has a lower freezing point, so the temperature has to drop further to get that ice to reform. And it's a lot harder to reform that ice with the presence of the salt. We could also put the salt on the sidewalk to prevent the ice from forming, because once the water starts to hit the sidewalk, again, it forms a solution and it has to get colder than 0 in order to freeze. Now, question 2, we're asked, why does antifreeze, which is ethylene glycol, why does adding antifreeze to water in your car engine help to keep it from overheating? So our car engines, if you've got a regular combustion vehicle, not electric, your car engines all have radiators, and those radiators have a mixture of antifreeze and water. Now, the purpose of that is to keep your engine cool, to keep your engine from overheating. Now, engines get very hot. They get to temperatures far above that water's boiling point. So what that antifreeze does is it lowers the boiling point of the water to keep that solution running through your engine. Now, at the same time, people who live in very, very extreme cold climates rely on that antifreeze to keep their engine from freezing. We want to keep that water from forming a solid block in our radiator, which would keep our vehicle from running. Now, our next problem is we're looking at our I values. Remember, I is that Van't Hoff factor. And that Van't Hoff factor plays an important role in the impact that the solute has on each of these properties. So we've got to determine, is our substance electrolyte versus non-electrolyte? And that goes back to things we reviewed earlier. What types of bonds do we have? Is this molecular or is it ionic? So if I've got magnesium bromide, magnesium's a metal. The instant we see that metal, I have an ionic compound. Soluble ionic compounds are electrolytes. So magnesium bromide is an electrolyte. If I were to break it into its ions, it's going to break apart into Mg2+ and 2Br-. Now we've got to remember what our chemical formulas mean. This 2 here, that tells me how many bromides I need to balance the charge of the magnesium in the ionic compound. It does not mean I've got a Br2 molecule. It means I have 2 bromides for every 1 magnesium. Now, I have 1 magnesium and I have 2 bromides. So when that MgBr2 breaks apart, it breaks into 3 particles. So that means that my I value here will be 3. Now, I've got this CH3, CH2OH. This is ethanol. It's an alcohol. Remember those alcohols from our organic chapter. This is a non-electrolyte. It's a molecule. It's all nonmetals. So as a non-electrolyte, if I have a non-electrolyte, its I value will be 1. Now, we will take a look in other videos at examples of how to actually calculate freezing point depression changes and boiling point elevation changes. So we'll see these I values come up. We'll look at our concentrations. We'll see how to find new boiling points or new freezing points, or how to find a concentration that we need to get a particular change. We'll talk about all of this with our colligative properties.